Good day, everyone. This is Claire Jane Fronteras, and today I'm going to discuss to you this simple Excel program I have created that will solve simple span beam problems. In this program, we have two ways in solving shear in beams. First, we can solve by using 2001 NSCP code. Second, we can solve by using 2010 or 2015 NSCP code. As you can see, in the leftmost corner of the program, we have the input or the given in the problem. Here, we should input the data that we will be needing in solving, such as the beam width, effective depth, the length of the simple span beam, the service load such as the dead load, included na dito ang beam weight, live load, and the point load as well. We should also input the stir-ups dimensions. The stir-ups acts as a transverse reinforcement of our beam. It is important to read the problem carefully for us to be able to identify the given in the problem. The table that we can see in the middle is the calculations for the 2001 NSCP code, and you can see the calculations in the table right part of the program for the 2010 or 2015 NSCP code. Let's start first sa 2001 table. We can see the outputs for the beam's ultimate uniform load, reactions in the beam, our ultimate design shear load or the VU, our VC, the shear stress of the concrete, and of course, our VS. By the way, in 2001 code, our P or the reduction factor is 0.85, while in the 2010 or 2015 code, the reduction factor or the phi is 0.75. Below, we can check if our section, we compare the VS. The VS must be less than or equal to 0.67 squared of FC prime times BW times D, so that we can confirm if the section is adequate to carry shear. And if not, we can adjust the beam size. We will be also finding the spacing of the stir-ups using this program. In the minimum shear reinforcement table, we compute the AV or the minimum shear reinforcement. We compare two values of AV and find the greater one. The greater value will be the minimum shear reinforcement. If our AV is larger than our minimum shear reinforcement, we can assume that the diameter of the stir-ups is acceptable. In finding the maximum spacing of stir-ups, we have to follow the right format according to its range. In the first bracket, will be 0 to 1/2 VC. If our VS falls between these values, we will have either D over 2 mm or simply 600 mm as our maximum spacing of stir-ups. We can choose either between the two that have the smallest value. If our VS falls between 1/2 of VC to twice of VC, we will have either of these three: D over 2 mm, 600 mm, or simply our computed spacing or the S in millimeter. If our VS falls between 2 VC and 4 VC, we will have either of these three as well: D over 4 mm, 300 mm, or the calculated spacing in millimeter, which is the S. But if our VS passes the boundary for VC, we are not allowed already to design. We are not able to find the S maximum. After this, we have the table of outputs from the program. Sample problem. Design economical spacing of 10 mm diameter stirrups for the beam which carries the factored loads as shown. Use Fc prime is equal to 21 megapascal and Fy is equal to 276 megapascal. We have here the given. So we have to input the rectangular beams data. As you can see, we have the beam's width or the base or the B, it's 300 millimeters. We have an effective depth of 536 millimeters and a total of 600 millimeter total depth. We have L, which is the beam length, total length of 6 meters. We have the Fy, which is stated in the problem, of 276 megapascal, and the Fc, also stated in the problem, 21 megapascal. We have here the service loads. We have dead load of 50 kilonewton meter, and let's assume included na dito yung beam weight ng beam. And the live load of 30 kilonewton meter. We have also a point load at the center of 150 kilonewton. So the stirrups dimension, it is stated in the problem that we have a 10 millimeter diameter stirrups for the beam. And we have 2 legs because as we can see in the problem, there are 2 leg stirrups that we can see. After inputting the datas, we have here the calculations. So, the W for the 2001 NSCP code is 121 kilonewton meter. We have the reactions, which is 438 kilonewton. The VU is 373 kilonewton. The VC is 122.8 kilonewton. And the VS is 316.18 kilonewton. Then, we're going to check if the section is adequate to carry shear. Vs must be less than or equal to 0.67 times the square root of Fc prime BWD. So, we have here the computed value of Vs 316.18 kilonewton. And this 0.67 square root of Fc prime BWD is 493.708 kilonewton. So it is adequate. I mean, it is true. So Vs is less than 0.67 square root of Fc prime BWD. So we can say that the section is adequate to carry shear. For the spacing of stirrups, we have 73.49 millimeters. So, we must compute for the minimum shear reinforcement. AV is 157.08 millimeters squared. The AV minimum 1 is 22.6972 millimeters squared, while the AV minimum 2 is 27.9602 millimeters squared. We must get the greater value. So the greater value is AV minimum 2, which is 27.9602 millimeters squared. Therefore, assumed diameter of the stirrup is acceptable. For the maximum spacing of stirrups, we have 3 ranges from 0 to VC over 2, VC over 2 to 2VC, and 2VC to 4VC. So, must compute first for the values of VC over 2, 2VC, and 4VC. So, we have computed these 3 values. So, we must determine if our VS, where does our VS falls. So, our VS is 316.18. We can say that our VS falls to this range 3, from 245.626 to 491.252 kilonewton. So we must select for the lesser value from these three, which is the 73.4953. So we must use the S. So let's say this S max is approximately 70 millimeters. Then we can locate the first stir up, which is in 17.5 millimeter. For the output of 2001 NSCP code, we have the excess here in millimeters. It is in ascending form. So as the X ascent is increasing, the VU is decreasing, as well as the VS and the S. So we determined the value of N, or the number of stir-ups to be placed. So we can say it's approximately 7. Here, 7 as well. And for the third one, we have 14. For the 2010 to 2015 NSCP code, we have WU 108 kilonewton meter, reactions 399 kilonewton, VU 341.112 kilonewton, VC 125.269 kilonewton, and the VS 329.547 kilonewton. Now let's check if the section is adequate to carry shear. VS must be less than or equal to 0.67 times the square root of FC prime BWD. And as you can see, it is true and correct. So we can say that the VS is less than this value. 329.547 is less than 493.708 kilonewton. So let's proceed. The spacing of the stir-ups, we have here 70.5142 millimeters. For the minimum shear reinforcement, AV, we have 157.08 millimeters squared. The AV minimum 1, 21.7766 millimeters squared. And for the AV minimum 2, 26.8261. You must find the greater value of these two. We can see it's 26.8261, which is the AV minimum 2. Therefore, the assumed diameter of the stir-ups is acceptable. For the minimum spacing of stir-ups, we have three ranges as well. The VC 0 to VC over 2, VC over 2 to 2VC, and 2VC to 4VC. We can see that our VS is 329.547. And as we can see, it falls in the third range between 250.539 and 501.077. So we can say that it's either of these three values. So we must pick the smallest one, which is the 70.5142 millimeters, or simply the S. So we can say that our S max is 70 millimeters. The location of first stir up is 17.5 as well. So for the outputs of 2010 to 2015 NSCP code, the X, which is our depth, effective depth, and the 1000 millimeter and 2000 millimeter. So as the X is increasing, our VU and as well as our VS and is decreasing. Yes, it's decreasing. But our S is increasing. For the N, which is the number of the stir-ups to be placed, we can say that for in 536 millimeter, we have 7. For the 1000, we have 7 as well. And for 2000, we have 14. Thank you for listening. God bless. Bye.